I'd like to first thank Alessandro for inviting me to give this talk, and also particularly for coming up with this cool title for my talk. I felt like I needed to at least make an effort to sound like an expert on the topic I'm talking about. So the first thing I did was to look up the word quintessential, and apparently it means representing the most perfect or typical example of a quality art class. So the good news is that, I'm happy to learn that I'm working on a quintessential computer science problem. Maybe I'll change my webpage to call myself a quintessential computer scientist. But I also want to mention, not only is consensus a quintessential computer science problem, it should also be a quintessential crypto problem. I think maybe majority of the audience here are from crypto community, and we know that, for instance, this amazing line of work on multi-party computation basically assumes broadcast channel as given, and the work on consensus is trying to open this box and try to solve the broadcast problem. And for this reason, when we submit consensus papers to crypto conferences and also to ePrint, they should not be rejected because it's not a quintessential crypto problem. Okay.
Just for a comment, this is not new. A lot of the work of in multi-party computation was how to use private channels to achieve this, for example, to achieve broadcast. So it's really not a...
Sure, I mean, not all of them assume broadcast as given, but a lot of them...
No, what I'm saying is that using cryptography to achieve broadcast is something that's sort of...
Oh, yes. So also a lot of these consensus protocols use crypto as a building block, like signatures and hash functions are often used. So there's a very deep connection between consensus and multi-party computation protocols. Okay. So I'll be pretty short on the motivation, right? We know all these decentralized cryptocurrencies, Bitcoin, Ethereum. What enables these fully decentralized systems is a core abstraction called distributed consensus, and that's what we are going to discuss today. So the plan is the following. I'll start with explaining single-shot consensus, often called Byzantine agreement. I'm going to go over some classical upper bounds and lower bounds. And then in the second half of the talk, I'm going to talk about blockchain constructions. So blockchain is like repeatedly reaching consensus over time, whereas single-shot consensus or Byzantine agreement tries to solve the consensus problem once.
In the distributed community, consensus mathematically has been realized over the years that just from the mathematical point of view, consensus means we agree on one thing. Suppose now we have 10 proposals and we agree on 2 things. Does the mathematics, the algorithms, distinguish between agreeing 1 and 2? And in some way, in some mathematical way, the mathematics do not distinguish between the 2. And the only question is, as human beings, does the question of consensus agreeing on 2 things has any value? So perhaps I never thought about, perhaps in blockchain it can eventually, but
That's a very good point. Maybe I can try to talk about this when we go to the second part of the talk. Like, why is it interesting to have a blockchain as an abstraction? So maybe you could remind me in the break again to talk about it in the second part of the talk. And I think Raphael in the afternoon will also try to motivate the blockchain as an abstraction. Got it too. Okay. Well, if you have any questions, please feel free to interrupt. And the more interaction, the better. So essentially, if you look at the talk, I'm going to start by talking about results from the 1980s. These are classical results. And then I'm going to talk about some very new work that very recently came out, but still of a classical nature. But maybe I'm going to try to use one blockchain protocol to try to also One is to try to answer some of the theoretical questions that's raised by the first part of the talk. And then, but this also, hopefully I can provide some practical perspective on how to implement these blockchains too. Okay, so what is Byzantine agreement? The definition was proposed in the work by Lamport, Peace, and Shostak in 1982. Imagine we have n generals, and among them, one is the commanding general. So these generals would like to reach agreement on whether they want to attack or retreat. Okay, and then essentially, the commanding general receives an input, right? He makes a decision whether we want to attack or retreat, and he wants to broadcast this value to everyone. The problem is that there's no native broadcast channel. Had there been a native broadcast channel, like the radio or something, he could have just like shouted out loud on the radio. Instead, we are going to have a modern version of the problem where the generals communicate with each other over email. So they can send emails to each other. They have good security best practice, like they use PGP to encrypt their email so I can authenticate where the email is coming from. And if an honest general sends an email, then an honest recipient will receive it on the next morning. So let's say the generals, they each have a clock, and when it's like past midnight, they wake up and they check their email. Okay. But the problem is that some of these generals are corrupt, like they're traitors. And these corrupt generals, they're trying to disrupt the agreement. Like for instance, if the honest generals, they end up deciding on different things, like some attack, some retreat, then this can cause casualty. Unfortunately, the commanding general can be corrupt too. Like if the commanding general were honest, he could just like send the same bit to everyone, and then everyone listens to the commanding general. Any questions about this problem? So maybe to understand the problem a little bit better, let me first formally define the security requirements. First, obviously this is an agreement problem, so we want consistency. Consistency requires that all of the honest generals output the same bit. Okay, if you and I are both honest, you output B, I output B prime, then B must be the same as B prime. We are going to assume that the execution can be randomized. Like for instance, a lot of these protocols use digital signatures and stuff, like the signature could be randomized. So we want these security properties to hold for all but a negligible fraction of the execution traces. In fact, actually, for the purpose of this talk, we are mostly just going to use signatures and hash functions. So if you are happy to assume that it's like an ideal signature or ideal hash, then you can basically pretend that all these properties must hold with probability 1. Okay. So if you just only want consistency, then it's not really an interesting problem because everyone can just output a canonical output 0, and then they're always guaranteed to have consistency. And to make the problem more interesting, we require also validity, which says that if the commanding general is honest, then all of the honest nodes output must be the commanding general's input. So this makes the problem non-trivial. So to understand this abstraction a little better, it helps to look at some strongman solutions and why they don't work. The first strongman solution, obviously, is we could all just listen to the sender. I'm also going to call the commanding general a sender, because the sender wants to broadcast this message to everyone. Like the problem here is that we want to essentially realize a broadcast channel, but we are only given pairwise communication channels. Okay. Well, obviously, why doesn't this solution work? Obviously, this doesn't work. And why?
You could send the different bits.
Right, so if the commanding general is corrupt, then he can just send different bits to different people, and people will end up outputting differently. The second solution is majority vote. It's also a very natural protocol, right? So this first strongman says, we shouldn't just listen to the command in general. Perhaps we want to collect everyone's sentiment. So here's a natural protocol. The sender in round 1 sends its input, B, to everyone. And then when I receive the bit from the sender, I'm going to vote on the bit I've received. If I receive 2 different bits, like maybe let's say I just vote on the first bit I receive, and my vote is basically a signature on the bit received from the sender, and I'm going to broadcast this multicast, basically send this vote to everyone. And then in the third round, we collect all the votes, and we basically count the votes for each bit, and we are going to output the bit with more number of votes. Okay, maybe let me be a little bit more precise. Let's say whatever has more votes, I'm going to output. So the question is this protocol secure?
This is different.
The screen doesn't like the protocol, obviously. It's taking a long time to load. So what do you think of this protocol? This seems a little bit better than the first strongman, right? Because now we are not just like relying on the single guy being honest.
If the majority is corrupt, then they can, if like more than half of the nodes are corrupt, then they can change things around.
So if more than majority are corrupt, like they can vote differently to different people. But in fact, I claim that this protocol does not even defend against a single corrupt node. Just imagine this is like compare and output the bit with more votes. So, but in fact, it doesn't actually even defend against a single corrupt node. And for instance, here's an.
This is the first. You have a single corrupt node. This is the first algorithm that solves the problem.
Okay, let's go over this attack together and see whether it works.
In the whole system, there is one corrupt. It's either the general or the commanding general or one of the rest.
So let's say the sender is corrupt.
If the sender is corrupt, then all exchange, they are honest, and they ignore what the sender. They ignore the sender. You don't look at what the sender said. What the sender says.
So let's look at this attack. So maybe there's P1 and P2. There are 3 parties.
Pardon?
Let's say there are 3 parties. Maybe let's say there's n.
You have to have at least four processors.
Let's just assume P1 is a collection of n parties, and P2 is a collection of n parties, and the sender is a single party. So in total, n is equal to 2n plus 1. N is the total number of parties. So let's say in the first round, the sender will send 0 to this guy and to these people, and he sends 1 to these other people. So now everyone will vote. And the red is the vote, right? So now, obviously, these people will vote for 0, and these people will vote for 1. And these votes are broadcast sent to everyone, right? So obviously now, when you count exactly m votes for 0, and then you're going to count m votes for 1. And then basically, the sender is going to be the tiebreaker. So what he's going to do is he can vote for 0 to these guys, and he can vote for 1 to these guys.
Ignore the sender.
But they don't know that he's malicious.
What?
They don't know that he's malicious. Always ignore the sender.
Always ignore the sender.
But that's not what the protocol says.
So I mean, like if you always ignore the sender,
Assume 4 processors.
if you always ignore the sender, the protocol may not have termination because let's say there's an even number of people in this case.
So it will have validity, right? Just ignore the sender on the voting.
We want to have also, it's implicit that we always want to have termination, like the protocol must output something, like at the end of, let's say, a fixed number of rounds. Okay, so it's not allowed that people just don't output.
Okay, so
We need a sender to propose something at the beginning, otherwise there was something to want to do.
I'm sorry, it's all about the setting. The original setting was no signature and just sending. You know that if you receive from somebody, you got from this sender, and that's it. No signature, and therefore you need at most third corrupt, which means that if one corrupt, you have to have at least 4 processors, 4 people, not.
Yeah, we are actually going to do a lower bound.
We are going to a majority, so it's my mistake.
So yeah, we're actually going to go over that lower bound too, like without the signature, it has to be 4 nodes for 1 corrupt. So that's like the...
When one corrupt, you know the sender is the original algorithm.
Yeah, so that's going to be in the second half of the first part. Okay. But basically, I guess these are very good points. Like there are different variations of this kind of voting protocol. But I guess I only picked one specific variant. But I guess the point is to show this is not a trivial problem. Like none of these intuitive and natural protocols, like they don't necessarily solve the problem. We can analyze all these other variants too. So I mean, now what's next, right? A very natural thing to try is for people to keep comparing nodes, right? This protocol is like the sender sends something, we compare nodes, and we make a decision. But what about now we keep comparing nodes more and more to amplify the agreement? But the challenge is how to design a protocol that captures this idea. Like, we keep comparing nodes for more and more rounds. And therefore, I'm going to talk about a very simple protocol by Dolev and Strong. This is a very well-known result. The protocol assumes a PKI. And everyone knows everyone's public key, right? We are using PGP to secure our emails. I'm going to use the letter F to denote the number of corrupt nodes. Okay, so here's how the protocol works. So initially, every node has a set EI. So node I set is called E sub I, and the set is empty at the beginning. So in round 0, again, the sender is going to sign its input bit and send it to everyone. Now, for the next F+1 rounds, everyone's going to do the following. Let's say in round R, I'm going to look at all the signatures I've received for each bit. And if for some bit, I've heard at least R signatures from distinct nodes. These signatures must come from distinct nodes. And moreover, it must contain the sender's signature. So if this holds for some bit B, and this bit B currently this B is not in my set E sub I, now I'm going to do the following, because I've collected a lot of votes on this bit B. I want to sign this bit B star. Sorry, the bit is B star. I'm going to sign the bit B star, and I'm going to send the signature to everyone. But I will also include all the signatures I've heard so far on B star as well. Okay, and I'm also going to add B star to my set EI. Okay, so the key thing to keep in mind is that in round R, I'm always going to count at least R signatures. So in round 1, I want to see 1 signature from the sender. In round 2, I want to see 2 signatures, one of which must come from the sender. In round 3, I want to see at least 3 signatures, one of which must come from the sender. If there's more, that's fine, but just basically at least R. Okay, so I'm going to repeat this for F+1 rounds, where F is the number of corrupt nodes. If you don't know the number of corrupt nodes, you can just round it for N+1 rounds, where N is total number of nodes. Okay, but let's imagine now we are aware of an upper bound on the number of corrupt nodes. And at the end of round F+1, we are all going to make a decision. And the decision is very natural. I'm going to look at my local set. And if the set has only 1 bit, I will output that bit. Otherwise, if the set is empty or if the set has both bits in it, I'm just going to output some canonical output, 0. Like in the case where my set contains 0 or 2 bits, in some sense the sender must be corrupt. And in this case, we don't need validity, and we can just output some canonical bit. If the sender is honest, essentially at the end of the protocol, every honest node set must have size 1, and we are going to output the sender's input bit. Any questions about the protocol? If not, I'm going to go over the proof. It's a very simple protocol. Okay, so why does this protocol work? The first thing to see is the following claim. If in some round R, let's say some honest node I.
So wait, sorry, when you say work, against how many corruptions? So what?
And this actually works against an arbitrary number of corruptions so let's say F is arbitrary number of corruption, as long as I run the protocol for F plus 1 rounds.
Okay, so you know what the number of corruptions, it's a matter of the run.
If you don't know, you can just run it for N plus 1 rounds, right? And N is always an upper bound on the number of corruptions. Okay. So the first thing to observe is that if in some round R, some honest node I has the bit B in its local set, then it must be the case that in the next round, everyone has the bit B in their local set. So if I have something in this round, you'll have it in the next round. That's what this lemma says, assuming we are both honest. Okay. You must have it in the next round or before that. If you didn't have it now, you must have it in the next round. So, okay, so how do we prove something like this? It's very simple. Node I is honest, right? So if node I has bit B in its local set, remember the protocol, whenever I add something to my local set, I'm always going to share all the signatures I've seen, including my own signature. Like I also add my own signature to it, and I'm going to broadcast this to everyone, right? So think of the moment at which node I adds this bit to its local set. Let's say it was added in some round R prime. So it must be that node I has seen at least R prime signatures in the round R prime. And in that round, he's going to add its own signature, and he's going to broadcast all these R prime plus 1 signatures to everyone. So therefore, in the round R prime plus 1, everyone, if they had not added the bit to their local set yet, they will, of course, add it in the next round. So very simple proof. It just says, if I know something now, you'll know it in the next round. Okay. I think maybe this is sorry. The numbering is a little weird. So this is, I was going to call this claim 1, and then this, let's call this claim 0. Okay, so the next claim to observe is that something magic happens in the last round. If an honest guy I has the bit B in its local set in the last round F plus 1, then it must be that every honest guy has the same bit B in the last round. So now this is talking about simultaneous. If I have it now, you must have it now. And this holds for the last round. So that's why there's something interesting happening here in comparison with the previous claim. And why is this true? Okay, so essentially, if in round F plus 1, let's say if I has added B in some prior round then already, by claim 0, already everyone must have it in the next round. So the only case we need to care about is if I added this bit in the last round. Right? So if I actually added this bit to its local set in the last round, it must be that I has seen F+1 signatures, at least F+1 signatures in the last round on this bit B. And because there are only F corrupt nodes, at least one of these signatures must come from an honest node, right? So think about when that honest guy signed the bit. This must have happened in a prior round. Let's say in some prior round R prime, this honest guy signed the bit B and added the bit B to its local set. Then it must be that in round R prime plus 1, that everyone has the bit B in its local set. And this follows from claim 0. And the interesting thing that's happening here is basically if I see F+1 signatures on the bit B, then one of them must come from an honest node. And this honest node must have signed it in a prior round. And therefore, in the next round to that round, everyone will have it. OK. Any questions? OK. So now we can kind of think about this protocol and reflect upon it, right? So one thing about this protocol is that if there are F corrupt nodes, by the way, maybe I didn't make it clear. Like throughout the talk, I'm going to assume corrupt nodes can behave arbitrarily, like they can deviate arbitrarily from the protocol.
If you can pinpoint, what was the place exactly that we used the signature?
Yeah, that's a good question. So where is this place where we use signature? This one doesn't need to use.
Here we didn't use the signature.
We didn't use signature security. But in this proof, when we say, OK, suppose I've seen F+1 signatures, one of them must come from an honest node. Here we are using signature security because if corrupt nodes, adversary can forge honest node signature, then it could happen that that honest guy didn't sign this bit and multicast it to everyone.
No, suppose that if sees F+1 signature, if I replaced it, if I receive F+1 messages on B from distinct node in round F+1. So instead of saying signature, I will just say received from F+1. And when I receive from somebody, I know that this somebody is that somebody. So if I have point-to-point communication and I replace the signature, it looks like you didn't use the signature. And so it's some magic, as you say.
Yeah, so that's a very good question. So what if you don't have signature and you change the protocol to saying you have to change the protocol because here
F+1 signature to F+1 nodes. I have from F+1 nodes this bit.
Yeah, so like the current protocol relies on the ability for people to transfer the signatures, right? Like if I put it to my local set, I'm going to tell everyone all the signatures I know. So it relies on the ability to like relay these signatures.
The signatures you know, and where did you use it in the proof?
What do you mean point-to-point communication? What do you mean I know that you sent the message?
That's the
Suppose that when I send to you, you know that it's from me because we have a dedicated line of communication.
Yeah, but somebody could have cut the cable and replaced the message in the middle.
This is the model is you have authenticate channels. Those are two different.
Okay.
So the issue is when you forward, you don't know.
Oh, you can forward messages.
Correct. So signatures currently let you forward messages and you can believe them.
Okay.
But without signatures, you can only believe things you receive on your own channel.
Okay.
Yeah, so like if you look at the first claim, it relies on the fact that if I know something now, I'm able to transfer all my knowledge to you. Like I can demonstrate an evidence. Here's why I have added to my set, and I'm going to add my signature to it, and then you're going to add it in the next round too. If there is no signature, I guess you can.
So here you're using it because if I have it, I have F+1 signature, and I'm forwarding the F+1 signature, so this guy will have the F+1 signature, and you don't have to rely on, okay, so here is the signature, right? In the honest, if the honest now heard from F+1, and he's forcing everybody because he's forwarding F+1 signature, so all the honest now will see this bit. This is the place.
What are the assumptions in the topology of the network?
It's point to point. It's pairwise channels.
But, no, but I mean, it's not fully connected necessarily, right?
It's fully connected. So everyone can send email to everyone else. Like, let's say everyone knows everyone else's public key. I can send a message directly to you by signing the email to you.
So what's the reason for relaying if it's fully connected and everyone can reach everyone in one step?
I guess the challenge is if a corrupt node.
I can sign something, send 0 to you, so I can send.
Yeah, so honest nodes, when they send message, they're going to send the same message to everyone. But if I'm a corrupt node, I don't have to do that. I can send you 0, and I can send Raphael 1. So if you are going to make a decision relying on my message from the previous round, unfortunately, you may not reach the same decision, right? Because I can send equivocating messages to different people if I'm corrupt.
Right, so essentially what's happening is that you're looking at this attack and you're saying, well, with signatures, if I'm in P1, I can just send whatever the sender sent me to P2. Like, okay, this is what the sender told me, plus their signature.
Yeah.
And the other guys are like, oh, this is what the sender sent me, plus their signature.
Yeah.
So we have kind of figured out that we should be ignoring the sender. But we can't resolve everything in one round, so we're just adding more rounds and plus some smart ideas.
Yeah. So we looked at this one round voting protocol, right? We compared nodes once, and that didn't quite work.
Right.
So what made it work here is that you have to apparently compare nodes multiple times. And in fact, you have to do it for F+1 rounds. But this is a very interesting question. And in fact, if without the signature, I'm going to prove a lower bound next to show that you actually have to have a...
This is the exact place of the signature.
Right. Okay. So this protocol has F+1 rounds, as you can see, right? You have to compare nodes F+1 number of times. And in fact, this is somewhat inherent. And there is I think this was also proven in the Dolev-Strong paper, but the proof was rewritten several times and simplified by later work. So there is a well-known lower bound that showed for any deterministic protocol, it has to incur F+1 rounds to defend against F corrupt nodes.
This is even for fail stop.
This is, even for fail stop. Very good one. And the proof works in the ideal signature model. Even if the signature is randomized, if you're using the signature in a black box way, this lower bound still holds. Okay. So this is both good and bad, right? It's good in the sense that we have a protocol that can defend against arbitrarily many corruptions. So very strong security, but on the other hand, it's kind of expensive because we have to, repeat essentially linear number of rounds before we can reach agreement. And therefore, a very natural question is whether we can overcome this lower bound with the randomization. And this I'm going to try to save to the second part of the talk. Like when I talk about the blockchain construction, I can revisit this question. The answer is yes, obviously. You can do expected constant number of rounds. Okay. Like I said, the protocol is nice in the sense it defends against majority corruption, but it's not so nice in the sense that we have to assume a PKI, and people have to be able to sign messages. So now the question is, can we get rid of this PKI, right? Do we actually have to have this assumption?
You won't be able to do constant rounds for F+1.
I guess there's a lower bound that it's not clear. I think the only known lower bound is like for any there's a paper by Katz et al. That showed that you need omega n to n over f number of rounds, I think. N over, is it n minus f? Let me think. Maybe it's n minus f. So like if f is a half of n, you need at least constant number of rounds, so that's not too interesting. But if f is very close to n, then you need linear number of rounds.
The answer here is not just yes or no.
Yeah, it's more complicated. So, but at least we can hope, let's say, for, let's say, honest majority, the question is whether we can do. So this lower bound says if f is, let's say, a half n, any deterministic protocol must incur a linear number of rounds. But the lower bound is saying, okay, if f is like roughly half of n, maybe we can do constant number of rounds. So can we actually achieve that with randomized protocols? Okay. So can we remove the PKI? And this is like what you have been asking. So it's a very good question, and let's try to understand this question first. How much time do I have? Maybe 20 more minutes for the first one?
20 minutes.
Okay, so I think we can go over this. Oh, before that, I want to, before I conclude the Dolev-Strong, I want to mention a nice riddle. It was originally presented by Moses, Dolev, and Halpern in this nice paper. It's a way to understand common knowledge, and it's kind of remotely reminiscent to the Dolev-Strong protocol we have seen, right? So imagine there's a village, and they have cheating husbands and violent wives. It may not be politically, not saying that it's politically correct, but I'm just presenting it in the way that was described in this paper. Maybe next time I give a talk, I'll portray women as cheating and men as violent. Okay, so here's the problem. So in this village, the men may be cheating on their wives. The wives, they gossip, so they kind of know whether other people's husbands are cheating. They don't know whether their own husband is cheating or not. So one day, some outsider comes into the village, and he announces, there is at least one husband cheating in the village. Okay, so now the wives, every night, if the wife discovers that her husband is cheating, she's going to shoot the husband. Okay, so now the question is, on which day do the cheating husbands get shot? So this is a nice riddle.
That's one if you call them faulty.
Yeah, if you treat the cheating husbands as faulty, right? So imagine there are F faulty husbands, then they all get shot on the F day, essentially. And the reason is, imagine F equal to 1, there's only one cheating husband. So then, on the first night, this woman whose husband is cheating, she's going to discover that she sees that no one else's husband is cheating, and she's convinced that her own is cheating, so she would shoot the husband. So now we can do for F equal to 2, right? If no one gets shot on the first day, then we know that F is at least 2. So on the second night, if a woman discovers that among everyone else's husbands, only one is cheating, then she knows that her own is cheating, so she would shoot the husband on the second day. So you can do it inductively. And essentially, they all get killed on the F day.
You have to start with 2, not from 1.
Mm-hmm.
To start the induction from 2, because one cheating with whom?
Cheating with the others' wives. Okay. Well, they're not cheating among each other, I guess. Otherwise, it would be 2. Okay. So now, this is kind of reminiscent to Dolev-Strong, right? Because the magic happens in the F round, F or F plus 1 round. Okay, so now let's go to this PKI question. Do we actually need the PKI? So I'm going to prove a theorem that says, okay, maybe you could do without the PKI, but not with such strong security. And I'm going to show that if we don't have the PKI and there's only pairwise authenticated channel, then one cannot hope to tolerate 1/3 corruptions or more. And this is a well-known result by, I think it was first proven in the Lamport paper, but later on, the version I'm going to present is a simplified version by Fisher, Lynch, and Merritt.
But this does not, there are two aspects, PKI and probabilistic. So I think this result of the third just holds from deterministic.
This result holds for randomized protocols too.
Probabilistic too?
Yeah. Okay, so let's just revisit the model. Now we don't have the PKI anymore. So what's the difference? People can now send messages to each other. So let's say if Srini told me something, I'm not able to demonstrate the signature to you and convince you that Srini has said that. Okay, and the model is like still pairwise channels. We can communicate with each other, and I know where exactly the message is coming from. Okay, so how do we prove something like this? Here's a worthy try. It's not a correct proof yet. So imagine, let's turn back the wheel of time to 2006 when maybe Shafi was still in MIT. And let's say MIT wants to elect department chair. And the current chair, let's say back then, Srini, he makes a suggestion to Shafi and Silvio. So he decides the input and he sends the input to both these people. And now Shafi claims to, now these two people compare notes, right? So Shafi tells Silvio, Srini said Silvio. Like maybe none of them want to be department chair. They all want to focus on crypto research. So in this example, the key issue is like, because we don't have signatures anymore, like Shafi basically can claim whatever she wants about what Srini said. And Silvio, in this case, cannot distinguish whether Srini sent inconsistent messages to the two of them, or whether Shafi is corrupt, right? It could be that Shafi is corrupt and Srini is honest. Srini sent the same message to both people, but Shafi is lying. But it could also be that Srini is like, dishonest and he's sending inconsistent messages. So if Srini is honest, it must be the case that Silvio and Srini must both output Shafi, right, by validity. But if Srini is dishonest, let's imagine the protocol, outputs Silvio, because if it's like, let's say canonical output is Silvio. If not, we can flip the names around. So there is no way that this guy can distinguish which case it is. It's not a formal proof. Like for one thing, the protocol doesn't have to look like this. But it gives the intuition why this transferability might be important. Okay. So how do we make this proof correct?
You consider abort this model?
Yeah, it's a Byzantine fault, so you could just... Are you asking if the protocol, if this theorem holds for crash fault? I don't think so. The theorem holds only for Byzantine fault.
No, the FMLAs work also for probabilistic. It's a structural. You take the triangle and you're making a hexagon and everything goes.
Yeah. Yeah, so you said the key insight. Basically, the key insight is the proof is a hexagon, it's not a triangle. So what I did was a triangle, but it should be a hexagon. Like, I went to grad school with this friend, and whenever we go to an Indian restaurant, he would order a hexagon-shaped vegetable, and the waitress would be very, very confused. So this is how I remember the proof.
Yeah.
So here's how the correct proof works. I like this proof because it's very simple, but it's also, in some way, it's unintuitive. Because the first thing you have to be comfortable with is imagine a thought experiment. Like this is a hypothetical execution. We have 6 nodes. Like there's 2 copies of everyone, and everyone's running the honest protocol. So like for instance, let's say blue Srini, right? He sees that he's talking to Silvio and Shafi. This blue Shafi thinks she's talking to blue Srini and red Silvio, right? So the execution must be well defined. So this is not something that would actually happen in the real execution of the protocol, but let's imagine we kind of create an hypothetical execution like this, and we are going to use this hypothetical experiment to rule out protocols that defend against 1/3 corruption.
You don't have more to imagine. You just take a copy of the processors and connect it. It's a thought experiment, but it can actually be done. If somebody said I did it.
Sure, you could do it. Can be done. Sure, but this I think is like the most. To me, it's like the most unintuitive part of the proof. Like you have to create this kind of thought experiment with 6 nodes, not 3. And imagine we actually do have a protocol that doesn't use PKI and that it secures against 1/3 corruption. So one of these guys is allowed to be corrupt, and the security properties must still hold if only one is corrupt. Okay, so imagine now the red Srini receives the input 0, and the blue Srini receives input 1, right? So Srini is still going to act as the sender. Okay. So now let's reason about this hypothetical experiment, and we are going to think of it in several ways to reach a contradiction. If we can reach a contradiction, we can rule out such protocols. Okay, so the first way to interpret it, it could be that Shafi is corrupt, and she's simulating all this right-hand side in her head. And in this case, the red Srini and red Silvio, they're honest. Okay, now only one person is corrupt, right? So by validity, if we interpret the experiment like this, then both these people should output the bit 0. Any question about this? Okay, so if you are okay with this, then I'm just going to claim by symmetry, these 2 people will output 1. Okay, so that's not enough to reach a contradiction yet. Now, we can interpret the experiment in a different way. So imagine Silvio is the corrupt guy, and he is simulating this yellow part in his head. And now the red Srini and red Shafi, they're honest. Okay, so now we can use the validity property again, right? So if we view the execution like this, only one guy is corrupt. And by validity, the honest people must output the sender's bit, which is 0. So these 2 people must output 0. Now, if you are comfortable with this, then by symmetry, blue Shafi must output 1. Okay, so we are getting close. So far, we have only used validity. And to reach a contradiction, we have to use consistency at least once, obviously. So now, finally, let's view the execution as follows. Imagine Srini is the one who's actually corrupt. The sender is actually corrupt. And Srini is simulating this yellow part in his head. And in this case, the blue Silvio and red Shafi, they're honest. Okay, so only one guy is corrupt, and we must have consistency. So therefore, it cannot be the case that the red Shafi outputs 0, blue Silvio outputs 1, we have reached a contradiction. This basically rules out protocols like this, like protocols that don't use PKI but secure against 1/3 corruption. And the proof works for randomized protocols too. Like what I said is like assuming with probability 1, but you can, everything is reasoning about this hypothetical experiment. You can put in the probabilities and it'll still work with like a broad range of parameters. You can allow the protocol to fail even with like 1/3 probability, and there's still the lower bound.
Was it 1/3 or 1/4? Is it 1/4?
I'm sure. 1/3.
By majority voting, it's 1/3. You can do the calculation more carefully offline.
I just want to point out that this requires the adversary to simulate, in this example, 4 nodes. So this is under the model that the adversary has ability to have, say, polynomial simulation capabilities.
Yeah,
so, for example, in a proof of work situation, we don't assume that. So you assume a weaker adversary.
Yes,
then
that's
you can actually.
That's a very good point, right?
You don't need a PKI, right? So I mean, under the assumption that the adversary cannot simulate too many nodes.
Yeah, proof of work makes it, I guess if you assume each of these parties has 1 unit of computation power, then the adversary is not necessarily able to simulate 4 nodes in its head. The corrupt node is not necessarily able to simulate 4 nodes in its head. But in this case, I think a good point is, in order for the corrupt guy to be able to simulate these 4 nodes in his head, like if you had PKI, then you wouldn't be able to do that because, like for instance, Shafi could have a public key, and since Srini doesn't have the corresponding secret key, like he wouldn't be able to make the simulation in his head, and that's why the proof doesn't work if there's a PKI.
You might not have a PKI. You may not have any setup. But if the adversary is weak enough, then you can still, this lower bound will not hold.
Yeah, if you impose other resource constraints, then the lower bound may not hold. But you could maybe consider like variations of this proof, and you can prove other interesting things for, let's say, proof on work. Okay.
There is a relaxed question, a relaxed version of the consensus problem, which this does not strictly apply, in which the relaxed problem says, in a fail-free run, so that nobody failed, you have to agree. Otherwise, it doesn't matter.
Yeah, there's a notion called weak validity. Like in this example, there is a designated sender, and the sender is trying to broadcast. And in the agreement version, everyone receives an input. Consistency is the same as before, and validity, there are 2 versions. One is like, the stronger version is if all the honest nodes...
The stronger version.
They are subtly different. Like the stronger version in the agreement version is like, if all the honest nodes receive the same input, then everyone must output that bit. So that's called, this is the agreement version, and for this version, you basically automatically need honest majority. There is a weaker version that says validity only needs to hold if everyone's honest and everyone receives the same input. And for that, I think there's still a 1/3 lower bound, and that's proven in the same paper by Fisher, Lynch, and Merritt. The proof is an extension of this. I think you have to create a cycle of proportional to number of rounds of the protocol. It's a very elegant proof, so you guys can read the paper.
It's not for a constant error probability. So this gives you this allows constant error probability.
Yeah.
That thing you can do with 1 less epsilon.
Yeah, that makes sense. Okay. So I guess we can wrap up this part. It's good timing. We looked at the Strongman protocol. It assumes PKI, defends against arbitrary number of corruptions, but the drawback is it takes a long time to reach agreement. We kind of provided partial answer to the first question, right? Is this PKI necessary? It is kind of necessary if you want to defend against a lot of corruptions. But what I haven't mentioned is that So there is this lower bound that says we need 1/3. And indeed, it's actually possible to construct a protocol without a PKI that secures against fewer than 1/3 corruptions. So this is a tight lower bound. I'm not going to talk about the construction. So that's the first question we want to understand. The second question, I'm going to just save it for later. Like, I'm actually not going to directly try to answer this question. There's a line of work that tries to construct expected constant round protocols for the honest majority setting. I will, in the second part of the talk, I'll cover blockchains, and then I'll try to revisit this question. Okay, so we can take a break.